I'd like to welcome you all to the Thursday session of AofA and introduce Marie, who's going to talk to us about local limit of random discrete surfaces with or without a statistical physics model.
Okay. Thanks for the introduction, and thanks a lot for the organization. It's a pleasure to be here in Philadelphia and a pleasure to also share the works with people online. So what I'm going to talk today is based on joint works with Laurent Ménard and Gilles Schaeffer. And this is intended to be like a kind of a survey talk because it's maybe a bit outside of the typical subjects of AofA. So please do interrupt me either here or online if you have any questions or if something isn't clear. Okay, so what I want to talk today is the discrete surfaces, and what my discrete surfaces are in fact maps. Okay.
Oh, because I clicked away. I'm so sorry.
Oh,
Yes, try. Yeah.
And so before jumping really into the core of the subject, I want to give you a couple of definitions of planar maps, just to give you a feeling of the variety of topics in which they can appear. You can say a map, what we call a map, is a collection of polygons. So here a triangle and quadrangle and a heptagon, which are glued along the sides. So if you're at a big board, you can like cut these shapes into a very elastic material, and then you can try to identify their edges, like in the pattern I described here by the arrows. And if you do that, what you're going to obtain is like a surface, which is homomorphic to the sphere. And if you remember where you glued the edges, then you have like a graph drawn on this surface. And this is what I call a map. And here, because the resulting surface is a sphere, I call that a planar map. Okay. If all the polygons you started with are p-sides, then the resulting map is called a p-angulation. And this talk, I'm going to talk a lot about triangulation, where all the maps, all the faces are triangles, or triangulations, where all the faces are triangles. Just a side remark, not going to talk about that at all in my talk, but it's not clear at all that the surface you obtain is a sphere. In fact, it's not. And a very simple example with an hexagon gives you, for instance, here a map embedded on the torus. Okay, just to give you a bit of context here. Okay, so let me come back to planar map then. And in the rest of my talk, I'm always going to draw maps not on the sphere because it's slightly cumbersome, but on the plane. But this is really two equivalent point of views. And in fact, a completely equivalent definition of a planar map is to say that it's just the embedding of a planar graph on the sphere. Okay, and you consider two embeddings up to homomorphism, so that these two drawings represent in fact the same map. For those of you who are not familiar with these notions, I want to emphasize that this is a different notion from planar graphs. Okay, these two drawings here represent the same graphs. Neighboring relations are the same between the vertices, but they are not the same embedding. There is no way you can make this small edge here and I enter this face. Okay, and if you think back to the polygons gluing summary point of view, you can see that here I have, for example, in the middle a quadrangle, whereas in this picture here I have no quadrangle. Okay, so there are two different maps. And last but not least definition, a planar map is in fact a planar graph, but it has a bit more structure. And in fact, it's enough to prescribe the cyclic ordering of the neighbor of a vertex. Okay, so if for each vertex you give me the permutation, I mean like the cyclic ordering of its neighbors, then you fix completely the embedding. And it's a bit more combinatorial description. Okay, just a minor technicality here. All the maps are going to be considered going to be rooted that I mark a corner just to get rid of symmetry issues. And a very important point of view in my talk is that I want really to use map as a discrete metric spaces. And I can define a metric space in the following sense. The set of points are just the vertices of the map, and the distance between any pair of vertices is just the length of a shortest path between them. Okay, so between these two vertices, the length is 3. Okay, so this is very, very important. Okay, so I hope that this kind of short introduction about maps just made you realize that it's a different point of view. They are studied in many fields of mathematics and computer science and also statistical physics. We saw in the work of Harriet Walsh that there are some connection with representation theory and factorization of permutations, and they can be studied from many angles. But here I'm really going to be very specific and study them on a very with a very specific point of view. I want to look at the limit of random planar maps. Okay, and more specifically, I want to focus on the limit of random planar triangulations. So my model is going to be the set of triangulations of size n. So n can be either the number of vertices, faces, or edges. There is only one size parameter. And what I'm going to consider is just a uniform random element. So uniform random planar triangulation. Spoiler alert, in the second part of the talk, this distribution is going to change, and we're going to consider different distributions. Okay. And so if you, of course, we want to study Tn when n grows to infinity. And if you want to do that, there are basically two points of view you can consider, two different topologies for which you can study convergences. And roughly speaking, there is what we call a global point of view and a local point of view. So as n grows to infinity, the size of your maps become bigger and bigger. And so the typical diameter also grows to infinity. I mean, there is no like small world phenomenon. The diameter really grows to infinity. And so if you want to keep something which is like bounded, if you want to get a full picture, you need to rescale the distances. Okay, it's a very similar to like if we study like random walk converging to the Brownian motion, or like random Galton-Watson trees converging to the Brownian CRT. It's exactly this idea. And this is this point of view here. Like this is a simulation of a large random triangulations embedded in an almost isometric way in the space. And here there is a local point of view, which means that you basically sit at the root vertex and you only see what happens at a finite distance from you. So of course, it doesn't capture like the diameter, but it gives you some different kinds, some orthogonal point of views, and both are useful to study maps. And today I'm really going to look at this type of convergence. But before really going into this kind of result, I just want to give you a little bit the picture of the state of the art for this picture, because it will be useful at the end of my talk to give you a bit some connections and some perspectives about maps. Okay. So again, same model. Tn is just a uniform random triangulation of size n, and we want to rescale the distance, the size of an edge. So instead of considering really the graph distance, we rather consider the graph distance divided by a function of n, like n to the something. And there are a couple of motivation and results about it. So if you consider really a planar map as an embedding a discrete surface, as an approximation of a continuous surface, of course, if you want this approximation to be good, you want the mesh of your map, the mesh of your grid somehow to go to 0. And so if you rescale everything, you're going to converge to a smooth, a continuous random surface. So as I told you just before, it's also there are intrinsic like probabilistic motivations to construct a two-dimensional analog of the Brownian motion. It's a little bit what I said earlier. Like if you take a Galton-Watson tree of type n, we know that the height typically is a square root of n. There's a constant here, but I don't care really. And you know, if you rescale by square root of n, you have a convergence to one very a realization of the CRT Aldous Brownian tree. And so you can ask whether something similar holds for like random maps. Okay, in fact, that's been established by Mirmont and Degas that you do have such a rescaling, except that for maps, the rescaling would be like n to the 1/4 rather than sort of n, and they can prove that there is convergence to what they call the Brownian sphere. And there are some motivations also coming from statistical physics that I will describe a bit more at the end of the talk. And what I really want to emphasize on this picture is that there is a universality phenomenon. Okay, so no matter what kind of precise model of random maps you consider, like triangulations or quadrangulations or just general maps, or like whatever really, what your favorite P, and you take P angulations, there is convergence towards the Brownian map. I mean, there might be a constant here in the scaling. That's 0, proper constant in the scaling, but you're going to get the Brownian sphere as a scaling limit eventually. Exactly like for Galton-Watson trees, if you want as soon as you have an offspring distribution with a variance, you know that you're going to get the CRT as a scaling limit. Okay, so there's really this strong universality phenomenon going on. And I didn't cite, I mean, there have been a lot of work in the last 10 years, proving that the original result of Miyamoto-Indegal can be extended to many families of maps. And I didn't cite all the works about that, but there is a big growing and big literature. Okay, so let me come back to the point of view I want to really consider today, the local limits. So, in a sense, it's a slightly easier point of view. You don't rescale anything, you just look at a finite distance. And somehow the idea, a very rough idea, is that if you look only at what happens at distance, like, I don't know, like 10 from the root, where if the map is of size like 1,000 or 1 billion, somehow you cannot tell the difference. Okay, somehow what you can see at a finite distance from the root is going to stabilize. Okay, and this is the local limit point of view. Okay. Okay, again, it's a nice model of random discrete geometry. It has been studied initially by Angel and Schramm, and I'm going to come back extensively to the result. There are also some connection with some statistical physics model I'm going to describe later. And I want to emphasize that also a universality phenomenon. So here, of course, the universality is a bit less strong as in the previous part, because you can see in the limit, I mean, like this is a limit. And of course, you know that this is not a limit of random triangulations. Okay, clearly you can see the triangles here. Whereas in these pictures, if you're far enough, you cannot see that there are triangles. I mean, there could be a limit of triangulations or triangulations, you cannot tell really. Okay. But here, of course, the limiting object is going to be different if you consider like triangulation versus triangulations, for instance. But there is a universality phenomenon because, and this is a quantity which is going to be very important. If you look at the number of vertices at distance r from the root, then it scales as r to the 4. Okay, so let me write that down. So this is the ball of radius r on the map, the end thing. And this is a constant. And of course, I mean, these two exponents are very non-rigorous, but they are linked. I mean, if you think about it, if you have a very big map and you want to have a ball big enough so that you have everything in that, you need r to be equal to the diameter. And if the total size of your map is n, then r needs to be n to the 1/4. Okay, because n to the 1/4 to the 4 is going to give you n. Okay. Of course, it's non-rigorous because there are two different points of view, but just use them. There are no contradictions. Okay. And I want to put something else. I don't know what it's saying. Oh yeah, another point of view maybe. If you think about another model of discrete geometry, not random, so like this two, or any regular lattice, actually, you can see that the size of the ball is of order r to the square, I mean r square. And so you can see that there are very different type of geometry going on here. I mean, it's a bit more fractal semi object. Okay, so let me, because I'm going to talk so much about local limits, let me be a bit more precise about the definition of local limits for those of you who never met this notion before. So the idea is the following. So I consider like planar maps, and I'm going to look at the ball of radius r, so that the vertices which are distance less than r from the root and the edges between them. And given m and n prime two maps, erase.
Sure.
I just want to...
Three boards also.
Okay, yeah, put together. Thank you.
There are already.
Yeah, I'd be fine with this. Okay, so this is, say that this is m and this is prime. And I want to look at the maximal radius of balls on which m and n prime coincide. Okay, for r equals 0, the ball is just like the central vertex, so good vertex, so of course they are the same. And for r equals 1, this is just this part here and this part there. So for r equals 1, I cannot tell the difference between m and n prime. Okay, but for r equal to 2, you can see that you can see the difference. So r in that case would be equal to 1. Okay, this maximal radius on which of the balls on which they agree. And you just take the inverse of this quantity, +1 to avoid dividing by 0, and this gives you a distance on maps. Okay, very easy notion of distance. And I just want to make you realize that if you have a convergence for the local topology, say a sequence of maps converging to M infinity here, of course, by definition, it means that for all fixed brackets, at some point, I mean, there is n large enough such that the ball of this R is going to be the same for Mn and for M infinity. Okay, just by definition. Okay. And what it means is that either your sequence is constant after a while, it's not very interesting sequence, or necessarily M infinite has to be infinite. Okay, because otherwise there's no way, I mean, they can agree on very large balls. Okay, and this is why here, in fact, you can see that I consider, in fact, locally finite planar maps, but possibly infinite. I should have made that explicit here, sorry. Okay, so the limiting objects are going to be really infinite maps. That's all I want to emphasize. So let me give you some very easy first examples of local limits, and I emphasize that you should try to answer them by yourself. So here, a very simple example is a sequence of maps, just a line with n+1 vertices and rooted at 0. And what's the local limit of this sequence? You have 5 seconds. So we don't have the, but maybe you can monitor the answer online, right? Okay, so my students are more reactive. So of course it is the infinite line, positive infinite line rooted at 0. Okay. Another slightly more elaborate example, same maps, but now the root is chosen uniformly at random. Okay, so here, okay, so you get the Robin has it. Thanks. This is the B infinite line rooted at 0. Okay, and the reason why is that when you pick the roots with high probability, you're going to be far away from the extremity, and so you cannot see the boundedness, I mean, the finiteness of the line. Another example, and it's the last one, I promise. If you now have a circle with n vertices, I mean, again, the limit is going to be z, okay, rooted at 0. And this is just to make you feel that if you have very large cycles, you cannot see them. So now if the size of the cycle grow to infinity with n, you in the limit and going to disappear, okay, which somehow makes the local limit kind of sometimes a weak version of convergence, but it can be also very useful, and I'm going to discuss that. Okay, so these 3 examples are not very interesting because the limiting object here are all deterministic limits, so it's not very nice. And so I want to move to something which is just before reaching maths. A last example, the example of random trees. Okay, so I guess many of you already know this kind of results, but let me rephrase them. Say I'm going to consider the uniform measure on plane trees with n vertices. So if you'd rather think of that as Gauss-Watson tree with geometric distribution condition to be of size m, that's fine. And for instance, like mu4 is a uniform distribution on these 5 possible trees. Okay, and here are realizations for n equals 500 and n equals 1000. So of course, somehow you can feel that if there is convergence, it's not toward a deterministic tree. Rather, it's going to be towards an infinite tree. I told you that it has to be infinite, and a probabilistic infinite tree. And again, much studied model, a lot of results. First one, I think, are due to Kasten. And now we have very precise results about what should be the probability distribution in trees, which are the offspring distribution. I don't want to give you too many details. The only thing I want to make explicit is that this tree is infinite, but somehow it grows to infinity in only one direction here. In another word, if you remove, if we remove all the vertices which are either like H, you're going to disconnect your tree into a family, into a forest of trees, and only one of these trees is going to be infinite. The other one are going to be. Okay, and so the result of Angel and Schramm I alluded to in my introduction is really the same type of result, but for uniform triangulations rather than trees. Okay, so they proved that if you consider now the uniform distribution and triangulation of size n, then you have convergence for the local topology to infinite measure, sorry, on infinite planar triangulation that they call the UIPT. Okay, and so yeah, and so there are some simulations of the UIPT here. Okay, so I want to give you a very short sketch, not sketch of the proof, but a sketch of a particular point of the proof. I mean, it's not the full proof, obviously, but just a one specific aspect of it. One of the key ingredients in the proof somehow is to compute kind of a finite dimensional distribution convergence type. So the idea is to prove local limit convergence, somehow you should be able to evaluate the probability that you observe a given finite neighborhood of the root. Okay, so say that you want to look at the probability that the ball of radius 2 is equal to these triangulations. Okay, and so this is not very complicated. If you want to prove that the if you want to, sorry, to compute the probability that the neighborhood of the root is that, somehow the only thing you need to do is you need to, so you have to start from this triangulation here, and you have to complement it with another triangulation so that to form a full triangulation of size n. Okay, so you have a first part and you need to glue another one. And the only constraint you have is that you have to be able to glue your triangulations together so that the boundary of your two sub-triangulations should agree. So I'm saying that there are triangulations. I'm a bit imprecise here. There are triangulations with a boundary. So I have make another drawing. I have one face here which can be of arbitrary degree, and then inside I do have only triangulations. Okay, a triangle, sorry. And okay, and if you do that, it's just the probability of that is just going to be the number of triangulation with the appropriate boundary condition divided by the total number of triangulations. Okay, so it's just really an enumerative problem. Okay, and explicit formulas, I mean, from Mireille's talk, we know that explicit formulas for these kind of triangulations are available. They are due to Brown in this setting, but really following the general methodology by Todd. And they are obtained thanks to catalytic equation with one catalytic variable, and they are very explicit, and you can compute explicitly the limiting behavior. Okay, so this is, again, this is not the full proof. This is one important aspect of it. Okay, and so what I want to say is that now the UIPT, the limiting object, has been much studied. A lot of works. It's a very well understood model of random geometry. I told you before that the volume of the ball of radius r curves are r to the 4, but we have actually much more precise estimates. And something I want to emphasize also that the UIPT is an infinite map, but it has only one end. So it's a property very analog to what I mentioned about trees, that if you remove, let me look at this picture, if you remove a subset of faces, say like the colored faces here, you're going to disconnect your map somehow, but all the connected components are going to be finite except for one. Okay, you only go to infinite in one direction in a way. Okay, and a corollary of that is that if you can embed UIPT in the plane without accumulation points, if you want. Yes. Yes, I'm going to come back a little bit to that picture. They correspond to the peeling exploration. So it's an exploration. I'm going to, okay, I can tell it now. It's an exploration of the map where you explore like in spirals around the root. And the colors correspond to the time of exploration. So the darkest, like the blue, are the beginning of the exploration, and not completely clear about the, maybe it's a rainbow order, but the, yeah, it corresponds to a paralleling way of exploring the maps. And this exploration has been crucial into proving the this kind of result, because you look at the time it takes you to explore the full thing until radius r, and it gives you some estimates about the number of faces you have to cross. Thanks. Okay, so a lot of result, and also a bit different type of result that the simple random walk is recurrent on the UIPT. Okay, so it's a very different model from Z2, but still you have some similar feature, which is a bit surprising maybe. Okay, and very important thing, universality. We expect exactly the same type of results to hold for other models of map, like triangulations. I mean, it has been proved actually for triangulations, for simple triangulations where you don't want any loops or multiple edges. And of course, we believe strongly that we can extend that to many families of maps as long as you have all the enumerative formulas. Okay, so which might be a bit more complicated to get for other families. Okay, and so for a while, I think people, and I'm included in these people, I've been a lot interested in proving some universality phenomenon to prove that we can have the same type of behavior for different families of maps. And after 20 years, I think we got bored a little bit and we wanted to show something different, okay, to see something different. In some way, what I want to describe in the second part of the talk is what does it take to see something different? What kind of models should you consider if you want to see a different type of behavior? Okay. Are there any questions so far? Speaking a bit fast, I think so. I have time for questions. Okay, if not, let me just do a small intermezzo. And it's why should we care about local limits? Okay, so there are quite difficult results to obtain, and maybe it's not completely clear to you what the point. I mean, okay, we are probabilists. We're happy to have convergence results, but apart from that, usually when you do, I think, analysis of algorithms, you're more interested in some convergence of parameters, like typically the size of the ball or this kind of asymptotics. And you could ask yourself, how does that help to have a full limit semi result, like result not only on some parameters, but really of the object. And the reason why it's very interesting to have this kind of result is that, of course, just by definition of convergence, if you have any functional which is continuous for the local topology, then you get for free the convergence of the f of gn toward f of g infinity if gn converges to infinity. Okay, but why is that useful? The main idea that the limiting object is often nicer, and usually it's easier to compute f of g infinity rather than f of gn. Okay, and for trees, it has been formalized by Aldous and Steele towards it's a very famous paper, the objective method. And we see, I think, a good illustration of this fact in Etienne's talk, where he could describe the independence number for finite trees thanks to results about infinite trees. And somehow in the infinite setting, you gain some independence properties in a way, which are very useful to compute g of infinity. Or also, but maybe the big cycle disappears, which is always nicer to compute things. Okay. And for maps, there are two such properties satisfied by the UIPT, which are very crucial when we want to obtain some estimates. So the first one is the one I already mentioned, the fact that it's one-ended. And so it allows to give a very neat picture of what happened, a very crisp picture. So if you remove some faces, you have connected components, and one of them is infinite. You really have a dichotomy between finite and infinite connected components. And this was really crucial to study this spinning exploration to get this kind of result. So this spinning exploration is what I said before. It's the spearboarding exploration. And to study that, it's much easier to do it really on the infinite map rather than on the finite maps. Sorry. And they also have what we call the spatial Markov property. And this means that if you remove, like, say, the ball of radius r from a map, what you have in the inside and the outside of the balls are independent. They only depend one from another through the length of their boundary. And again, this is only true in the infinite setting, because in the finite setting, of course, the total size should be equal to n, say, and so there will be some dependency. Okay. So it's a good motivation to study local limits on top of just studying limits, which is always cool. Okay, so let me now try to explain to you a bit more recent results about the local limits of a slightly different models of triangulations. So I think I really emphasize the fact that there is a universality phenomenon. And if you want to see different type of behavior, you really have to try summing. And it has been long understood, especially in the statistical physics literature, that if you want to see something different, what you have to do is what they call couple gravity with matter. What I mean by that is that you can think of your random map as like the metric space, okay, and you're going to decorate it by a statistical physics model. So in a more graph theoretical vocabulary, it just means coloring the vertices, basically. Okay, but it's nicer to say couple gravity with matter. You know? You have to sell yourself.
Thanks for that.
The translation, yeah. And then you can impress your friends. It's always nice. And okay, so let me first define the Ising model on a finite deterministic triangulation. So the Ising model has been introduced by Ising to model magnetism, and it's a very simple model, which is simple but exhibits a phase transition. Okay, so let's see what it gives for maps. So I start with the triangulation and I color the vertices, like in red or green, or plus or minus is more a statistical physics point of view with spin plus or minus. And you want the Ising model is just to sample a random coloring of the vertices with a probability which is proportional to this quantity. So maybe if you studied like Ising model, it should ring a bell. But again, combinatorial transformation, it just means it's completely equivalent to say that the probability of seeing a fixed coloring, you have a fixed parameter nu, and you get, so you fix a parameter nu, and then the probability to get a fixed coloring is just nu to the power of the number of monochromatic edges. So here I have a coloring, I have 5 monochromatic edges, so this precise coloring would appear with a probability nu to the 5. Okay, good. But the next step now is to sample a random coloring on a random triangulation. And you want to do that at the same time. So I don't want to first sample the triangulation, then the coloring. I really want to consider the full family of triangulations of size n with all possible colorings, so there are 2 to the n colorings per triangulation. And I want to sample at the same time the triangulation and the coloring, of course, with the same nu to the n to the number of monochromatic edges. Okay, so now I get just a probability distribution on colored triangulations rather than triangulations. Okay, and the Zn is just a normalizing constant here. And okay, this is now a probability distribution on triangulations with spins and colored triangulations. But if you look at the push forward, if you forget now the coloring, then it gives you a measure on regular triangulations, but which is different from the uniform triangulation, from the uniform measure, okay, except for nu equal to 1, obviously. But apart from that, it's going to be different. Okay, so it gives you somehow another distribution on triangulations defined with this notion of spins. Okay, maybe I'm going to write that down. So why are we doing that? So we are trusting our friends from physics, and we think that it's a good idea, but there is another way of seeing that in a more combinatorial setting. So I talked a lot about universality in the universality phenomenon in the limits of random maps. But actually, there is also a universality phenomenon on the combinatorial side of this story. And this was very, very lucky that Eva Myers gave a talk, because she explained us how we can see that universality phenomenon coming up from a equation with 1 catalytic variable. Okay, and if you don't remember very clearly, basically we know that if you look at maps, triangulations, quadrangulations, you name it, the asymptotic, the enumerative coefficients are all going to have the same asymptotic behavior. There is a exponential part and a polynomial correction in -5½ which corresponds to singularity of type 3½ if you look at the generating series. Okay, and this is true for like any reasonable model of maps if you want. Okay, what about Ising weighted triangulations? So now I want to consider the generating series of Ising weighted triangulation. So I have 2 parameters, my parameter nu here, which is the weight I put on the number of monochromatic edges, and t, which is just the size of the triangulation. Okay, so I just look at the generating series, I sum over all triangulation, and I sum over all the possible colorings, and I just get the weighted generating series by this Ising weight. So now this nu to the m plus c. And like 10 years ago, Olivier Bernardi and Mireille Bousquet-Melou proved that for every value of nu, Q nu t is algebraic, and satisfies, its coefficients satisfies this kind of behavior. I mean, to do that, they rely on the paradigm of analytic combinatorics as developed by Philippe Flageolet and Robert Sedgwick, and they obtain this type of behavior. And you can see that really it does take some effort to escape this -5 polynomial correction. For every value of mu, almost every value of mu, not in a probabilistic sense, almost every value of mu, you get this -5 correction, and there is one critical value of mu where something different appears, and you have 7/3. Okay. And let me also emphasize that this critical value of mu actually already appeared in the statistical physics literature by the work of Bulatov and Kazakov, and was also rediscovered by bijective constructions between Ising-weighted models of planar maps and some decorated trees, but not exactly in the same set. Okay, so this suggests strongly that we should observe a different behavior for nu equal to nu c. Okay. So let's try if we can do that. So what we proved with Laurent Ménard and Gilles Schaeffer, we in fact proved a result which is like fully analog to the one of Angel and Schramm I showed you before, is that if you take this measure of probability, then it converges in the local limit topology towards towards a measure on infinite planar triangulations decorated with pins that we call the new IIPT. Okay. Okay. Same type of results. So I want to give you again a small idea of the proof, again from a very specific aspect of the proof. And you need to do the same type of thing. You need to compute the probability to see a given neighborhood of the root. Okay, so again, what you want to do that, you want to count how many triangulations you can glue to make a full triangulations. But here things get more complicated because not only you have the length of the boundary should agree, but also the vertices on the boundary are decorated, they are colored, they're red or green. So they have to, the triangulations you glue have to satisfy the same boundary conditions. Okay. So what you need to do, rather than before, is really you need to understand the generating series of Ising-weighted triangulations, but this time with a fixed boundary condition. So if I come back to my picture here, you want to enumerate not only the triangulation with a boundary fixed length, but really boundary where you want to count how many. Not how many, sorry, the total Ising weights of, for instance, triangulations which are this type of boundary condition. Okay, so like what I call omega is really the word on plus or minus, plus minus. Okay, and so you have to do that for every possible omegas and prove that there is convergence. Okay. But it's completely similar. I mean, okay, just you need some more. Let me write down. The generating series of all the triangulations, all the spin configuration. This weighted generating series, and now I have Z omega, which is exactly the same, except that you only sum triangulation with a fixed boundary condition. Okay. So we obtain exactly the same result as Mireille and Olivier obtained for the Q, but specialized like omega by omega. Okay, it's just a refinement. It's not just, but it's a refinement of the result. Okay, and at this time, my plan was to do that. And but then Mireille's talk happened, and I felt like I heard her because she did such an amazing job presenting Tuts invariance that I should spend a couple of more slides to explain a bit more so yeah, that was not planned. So I'm going to try it. And yeah, I hope you get something out of it. So, okay, so we want to apply a 13 variance method. 13 variance from Mira's talk, you know that it appears when you have equation with two catalytic variables. Where are these equations? This is the first step. Okay. In fact, thanks to a kind of a combinatorial trick, it is enough to deal with like the full positive boundary conditions. Okay, because we know the result of Mireille and Olivier, and we can have a kind of a recursive. We have a trick somehow to do. So let's do it. Let's do the monochromatic boundary condition. So let's try to write generating series equations for this quantity. So again, these are all variations of this series, except that I change a little bit the boundary conditions. Okay, so all the spins on the boundary are colored red. I hope you can see color. And what can happen? Okay, so a very classical idea to enumerate maps, going back from plots, is to do the following. So you have a map, the boundary, and you do the following. So it's widget. You look at the root edge, which is the one following the root corner. And so this is the boundary. And here the triangulation triangles are here. And you wonder whether what does this triangle look like? So here you have a triangle. So you have already two vertices, and you need to know where the third, where the third vertex is. So you basically have three possibilities. Either there is no third vertex because your triangulation is in fact reduced to an edge. Okay. Or the third vertex is in fact belongs in fact to the boundary. This is the first possibility. Okay, and this is just a triangle, and here you have the rest of the triangulations, or the third vertex is not on the boundary. And because we're doing Ising decorated maps, you have two possibilities: either it's a plus vertex, a red vertex, or it's a green vertex. Okay, so that's good. So we can see how this decomposition translates into generating series. That should okay. There is problem with my file. Sorry about that. It should be nu t x squared. This is the easy case. Then here you have ax to the square, because if you have a triangle like that, you basically break your triangulation into two sub-triangulations, and you have to be a bit careful about how the perimeter adds up, but that's fine. Then you have a triangulation. So again, it's only positive spins on the boundary. So you're good. You just have to forbid these triangulations. The perimeter has to be of length at least 2. So you have to remove this term. Okay, still good. And just like because there is a minus sign here. Okay, so let's see what we can do. So what we can do, maybe we are a bit too optimistic by looking only at positive boundary conditions. Maybe we can go just one step higher and look at what we call Dobroshin boundary condition. It's physics literature, but actually just an arc of red vertices and an arc of minus vertices. And let's look at this new equation here. Okay, so now you have two catalytic variables, x for the number of red vertices and minus for the number of green vertices. Okay. Okay, and that's good because, sorry, if I have that, now I can fill in my generating series decomposition. Okay, but what is it good for? This is nice because I can do exactly the same decomposition as here, but now for S rather than for A. So again, I have the 4 possibilities, but what's very nice now is that you can see that there is some like stability, some property, and all the sub-triangulations that appear now have the same type of boundary conditions. So here it's just silly. Here you can see that you have an arc of red vertices and then an arc of green vertices, and here it's the same. So they are again enumerated by S. And here you split your triangulation into 2 parts. One is going to have a monochromatic boundary condition, okay, and one is going to be again a triangulation enumerated by S. Okay, so you can write. Okay, it's a bit messy, but really you can just write it down. Okay, so you need to solve the equation for S, and you can see that really there is no way of writing an equation without 2 catalytic variables. It's not that I'm aware of, but really it appears naturally if you want to decompose this. Okay, so what's good? So what's bad is that we have 2 catalytic variables. what's good is that we can see that this equation is linear in S here. Okay, there is no S2 square. Okay, so we can really proceed as in Mirai's talk, and we can factorize S and put everything in what's actually called the kernel, like that. You can rewrite the equation just like that. Okay, just a rewriting. And then we can see that we get the first pair of invariants basically for free by setting these two quantities. Okay, so maybe you forget a little bit what's the invariance, but sorry, that's a bit fast. Being a pair of invariants means that if you take this quantity here minus this quantity here and you divide by k the kernel, then you get something which has full of bounded order. And there is really a problem with my file. Sorry about that. And in fact, in this case, this quotient is just equal to 1. And so, of course, it has poles of bounded order. So you get invariance, the first pair. And then you have to find another pair of invariants. And things get a bit more complicated here. You really have to work with somehow this equation here and work with R. And somehow the very rough idea behind invariance is that you want to separate variables. Okay, so in R, X and Y, so if you look at my equation here, X and Y somehow are interlaced a little bit. And if you want to write that as pair of invariants, you really need to be able to separate the variables. So you have a lot of algebraic manipulations to do on Maple mostly to be able to do that. Okay, and I'm going to spare you the shape of the invariants. And when you have both pair of invariants, you're basically done, because you can then rely to the machinery I described, and you can combine these two invariants to get a pair of trivial invariants. And this part is easy. This part is really you kill the poles one by one in a very automatic way. Okay, the complicated part really here is to write to find the invariants. And this gives, okay, just using the standard machinery, this gives an equation with only one catalytic variable. And just to give you an idea of what it looks like, I have one a polynomial equation for A of X, which was the series I was looking for in the very first place. And it involves a polynomial in all these quantities. And this is the polynomial we get. Okay, so at this step, we are not fully done yet. But then we have like, we're in our comfort zone somehow. We have a lot of tools and to study and to be able to compute the asymptotic behavior of all the quantities involved here. Okay, so behind the result, there is a lot of, it's a really a combinatorial result in a way. I mean, the really hard part of the proof is there. Okay. Okay, that's all I wanted to say about the proof, and it's already a bit much. What I want to emphasize there is that we don't know much about the new IIPT, the limiting object. We know that it's almost surely one-ended. This is 8.3. We know that the simple random walk is recurrent, even for at the critical value, but we have no idea of what are the volume of the poles. Like it's conjecture to be different from R to the 4. But it seems really out of reach for the moment. And let me just try to explain to you why it seems out of reach. So I told you that in the uniform setting, without the coloring of the vertices, you need to be exposed to, there is this spiraling exploration. Okay. And when you do this spiraling exploration, you need to be able to control what's in the outside. So you need to be able to control this type of quantities for any omega. Okay, and we did that. But what gets messy here is that if you want to be able to really understand the building exploration, the spiraling exploration, you need to have a control when the length of omega grows to infinity, together with the size of the triangulations. So we are really into the realm of multivariate asymptotics, and I think Robin here is really the expert on that. And but here, like the type of scaling we have is different from the type of results which are available, and there is a lot of activity on this subject right now. So maybe it's going to be not so out of reach in a couple of years, but I think there are very strong obstacles to get something. Okay, so I want to conclude with a much more relaxed part, less technical. I just want to give you maybe some intuition of why we expect a different behavior. So I showed you the different combinatorial exponents, the -7/3 versus the -5/2. But I want to try to give you a bit my understanding of statistical physics behind these models. It's going to be very elementary. Originally, the AofA model was studied on D2, on the regular lattices. It makes a lot of sense because crystals are really ordered, and so it makes a lot of sense. And why do we study it on random models? I mean, not we love these type of things, but like why physicists want to study it on random metric spaces? So the idea, I think, I mean, from what I understand, is that in general relativity, the space, the underlying space, is not a regular lattice, but rather a Riemannian surface where the curvature gives the gravity. Okay. And again, very, very sketchy idea. There is this big challenge of modern physics, which is try to reconcile what happens at very large scales, like gravity, and at very small scales, like quantum mechanics. Okay. At large scale, we have gravity, we have Riemannian surfaces, and at very small scales, we have quantum mechanics, we have random things. I warned you it was going to be sketchy. And one attempt to reconcile these two theories is to consider the so-called UV quantum gravity model. So it looks like looking at replacing the deterministic Riemannian space by rather a random metric space. Okay, so it's why this appears. And in fact, the UV quantum gravity, it's a family of random measured space indexed by a parameter gamma. And there has been a lot of work in the physics literature and also in the mathematical and probabilistic literature about defining this type of surface rigorously. And here I just give you a simulation of the UV quantum gravity on the sphere for gamma equal to this value, which should correspond to the case of uniform maps without matter. And the dark part corresponds to points where there is a lot of mass. Okay, so you have very big mass. And here you have another picture of a model of random surfaces, which is the Brownian sphere I talked about in the beginning of my talk. And these two guys should be, in fact, the same object. So what I mean by that is that you know that the topology of this is a sphere, but you should be able somehow to blow it, to make it smooth, and to map it to the sphere. Okay, and if you do that, you should get that. And in fact, this has been done in a series of work by Duplantier, Miller, and Sheffield, where they proved that there is a correspondence between these 2 point objects. And their work is really in the continuum setting, really on the limiting objects. Whereas as a combinatorialist, for me, it would be much more natural or much more maybe make full of sense to have this kind of mapping, but on the discrete setting. What I would like to have is a random of planar maps converging to a limiting object. And on the map, I have 2 points of view. I have the distance given by the graph distance, but I also have the measure by just counting the number of vertices. Okay. The main obstacles here is that a priori maps are not, the embedding of a map is not canonical. You can consider different homomorphisms. Okay. But for some models of maps, we do have some canonical embeddings. For instance, we can, for simple triangulation without loops or multiple edges, we can embed them via circle packing. So the circle packing is just a configuration of circles like that, where you have tangent, and you can define a graph from that by just putting a vertices in the middle, I mean, at the center of the circles, and draw an edge between two vertices if and only if the corresponding circles are tangent. Okay, so it gives you a canonical embedding. So here, for instance, is the circle pack associated to simple triangulations of large size. And it gives you an embedding of the corresponding triangulations. And what we would like to have is the convergence of this picture to this one. That would be really nice. This is an open problem. This is not done, but for the record, there have been some very fantastic results in that direction for different type of embeddings, more complicated to describe by Albenque in 2020. So for the uniform setting, for the uniform distribution on maps, this picture is now, I mean, now it was in the physics literature for years, and now we have really a full understanding of it in the continuum setting, but also as a limiting of discrete objects. Okay, but this is only when you have uniform triangulations. But it's conjectured that all models, that maybe not all, but most models of maps decorated by statistical physics models should also converge to the gamma UV quantum gravity for other values of gamma. And there are some predictions about what should the value of gamma be. So, for example, the critical Ising model is believed to converge to square root of 3 LQT. Don't ask me why square root of 3, I have no idea. And similar statements, all for the model of decorated maps with a spanning subtree, like very combinatorial models of maps. Okay. And the LQG can be studied like without any connection with the random planar maps and just on its own as a measured on metric space. And a lot of properties are known. Okay, and so if we believe that all this framework work, that we have some connection, we have some convergence, then we could predict the volume of the bulb in the critical decorated triangulations from what we know to be true in the UV quantum gravity model. Okay, and this is why we think so these d square root of 3, which should be the volume. Well, if everything works, somehow it should be the exponent, this d of square root of 3. And it's known to all between these two bounds. So it should be different from 4. Okay, it's a very, very, very fast description of what's going on, but just at least that you know a bit what's going on, what's rigorous and what's not. Okay, and a lot of perspectives and related works are available for this model. We are very, uniform maps have been studied for a lot of 50 years now. A lot of results are available, and for maps decorated, much less results are available, but the field is rapidly growing. And we have a lot of nice problems, and I think it's very fascinating. So, of course, what I would dream to do is to find this volume growth. And I think we really need to get some more combinatorial description, finding some bijection with trees. Related work I did with Laurent very recently was to study the cluster. So the connected components of the pins of the same color. Okay, and we could exhibit that there's a very strong phase transition between the value of nu. Like this is what happens on Z2, but we have a similar picture on the random map. And yeah, more generally, I think it's a very nice subject. And I'm going to stop here.
Thank you. That was a wonderful talk.
Thank you
very much. Any questions?
Yeah, so this is my great talk.
Thank you.
And,
Means a lot.
Seems like really, good to have these methods. Essentially, I was trying to say something they know or even really suspect what should be true. And so this is great. But I'm wondering, maybe you already said it in talk, and missed it. When you have this special nu equals 1+7 in the evening decorated model, so then you show an exponent of a third, what things do you think either follow from that, kind of directly, or tell you intuitively ought to be true that are different for the critical model?
You mean like in the combinatorial description, or?
Well, you find that this exponent.
Yes.
So this is supposed to tell you that the critical model can behave differently from the side. But in what ways? In what ways do you see that and say, okay, I know it's different volume growth or like,
Yeah, it's a bit mysterious to me, to be honest. I don't have a clear, I don't have a clear feeling of what happened exactly. I mean, what I can picture, just talking, for the clusters now, we have a good understanding of what's going on and why this news plays a special role. And it's completely analog to what we have in Z2, like at the critical value. So we have things we can relate. But why the geometry changes at this point is a bit mysterious to me. The only thing I can maybe it has to change at some point in a way. And this is because when nu is equal to 1, say, it's a really the uniform setting. And so the decoration is really just Bernoulli percolation. So there's no way it's going to interfere with the geometry. And on the opposite side, when nu grows to infinity, somehow you're going to have like a completely uniform, I mean, only one color is going to survive. And so in between, there should be, there is somehow a transition, but I have no, really, I don't have, again, the only intuition I have behind that really implies some encodings, and it's not a direct somehow understanding. I can tell you a bit more, like when you could, like the map, decorated maps by some walks in the quarter plane, then you can see that the drift is going to be slightly different in the uniform models and here. But again, it's a kind of educated guess more than a really strong intuition. Sorry, that's a not very convincing result. Answer to.
You mean students should think about this?
Definitely. I think this is a key. We need to find a bijection, because all the works I mentioned, the links with UV quantum gravity, they do rely on some encodings with some maps in the quarter plane, like saying. Or we have to develop multivariate analytic combinatorics, much more. Say, I think we're in good shape.
I have a quick question. Who is T. Bud?
Timothy Bell is a mathematician / physicist from the Netherlands,
Okay,
and he has amazing works and amazing pictures.
so going to his website is.
His website is
Okay.
awesome. I mean, you have a lot of pictures. I mean, you can videos exploring maps. I mean, really, if you should visit his website. Amazing talks too.
I have a few related questions. I think you're welcome to share.
I'm fine. You should have the others actually.
Yeah, the first one is that field does state that for every boundary condition, and then you investigate the probability distribution on each. I was wondering, like, what's the influence of the boundary condition on the probability?
See, for the boundary conditions we consider, where the size of the boundary size, I mean, bounded, and the size of the triangulation grows to infinity, the boundary condition has basically no effect. If you want to see something different, you should have the boundary length growing to infinity together with the size. And results suggest, I mean, you can have a little bit of, it shouldn't matter too much as long as it's not growing to infinity too fast. But then I don't know. Then this is precisely what we don't know.
Yeah, so related to that, I think Keynote also mentioned that you use the Gaussian.
Yeah.
If I remember for the Gaussian condition, there is some regularity condition on how the boundary goes.
So this is true in Z2 because it's so fixed. In maps, somehow the fact that the geometry is random gives you much more freedom, and somehow it's easier actually, because I can do exactly the same type of decomposition I have here. And somehow studying the Ising model on regular lattices, it's actually much more complicated than on random lattices. Because on random lattices, you can somehow discover the geometry and the coloring of the vertices at the same time. You can have kind of a Markovian exploration, which makes everything much easier than you have a fixed prescribed geometry. So here we don't have any specific.
Thank you.
Okay, I guess we need to go to our coffee break. Thanks again. We're going to start again at 12:30.
All right, thanks, Conrado.